Welcome back, everybody. And the topic today is to continue this discussion about the mathematics of CNNs. And the thing which we are going to look at are specific technicalities like padding, stride, pooling, and other topics which are used in defining the architecture of a network. We're also going to look at how many parameters we get to train. And we are going to look at how this transfers into one, you writing your own code, because there are people here who want to write their own codes. But then all these parameters are typical parameters which you will use if you use either TensorFlow or PyTorch. So what normally happens is that people end up using either TensorFlow with Keras as an API, or they end up using PyTorch. Now, there is an example code here for CNNs, but typically these kind of codes which we hand tailor, they cannot often compete with the kind of speed you would get if you run on TensorFlow, with TensorFlow on Google Colab, or you run with PyTorch on dedicated machine learning machines. You should also keep in mind that you have access to machine learning nodes at the University of Oslo. You just search machine learning nodes, UIO, and then you apply for access. So, these nodes have actually installed both PyTorch, TensorFlow, and Keras. So you should be able to run codes there in case you're not too happy with the speed which your laptop gives you. Concerning TensorFlow and PyTorch, as we have said throughout the semester here, we do have textbooks which are very, very good. So one is obviously Rashka's textbook, and you can download the Jupyter Notebook from chapter 14, which is a PyTorch implementation of a convolutional neural network. Then, if you go to David Foster's book on generative learning, you can click on these links, and that brings you immediately to the GitHub address. And there, from there, you can, from chapter 2, there is an example on how to use convolutional neural networks. These books, like Foster's book, is a book which we will use a little bit more when we come to generative models. But for now, both for recurrent neural networks, autoencoders, etc., then Rashka's textbook is often the one which fulfills many of our own needs. So in brief, as we discussed last week, a CNN contains what we normally call a convolution stage, which is normally split in 3 parts. There is a convolution, the mathematical operation itself, and then this is sent through a so-called detector stage, where you actually massage the output through an activation function of the type, the ReLU function. And then you reduce further the dimensionality of the problem by a pooling stage, which we will also discuss a little bit more in detail today. And then when this has been done, you would typically flatten the output into just a one-dimensional array, which is then fed into a standard feed-forward neural network. And that one is the one where you just plain apply a dense affine transformations and then perform the rest of the training. So there are parameters of the weights and biases which we train in the convolution stage, as you will see today. And then there are weights and biases, that means parameters we train in the standard neural network stage. So this is the basic setup of a convolutional neural network. And what is often done is that you start with an image here, which could be 28 times 28 pixels, multiplied with one color channel. So this would be a grayscale image, for instance. And you can have many convolutional operations. So what often happens is that you apply a filter, which is in this case a 5x5 filter, but you produce 32 new images. So what happens is that you often don't downsize it dramatically in the first stage. from experience, one sees that if you were to downsize it immediately, then you will lose a lot of information. So what often is done then is to make many replicas, and these replicas are often set up as powers of 2. And then you may have a pooling stage where you reduce the dimensionality further. And I will try to explain to you what these parameters 2 by 2 mean, so that when you are setting up your own using, let's say, TensorFlow or PyTorch, or if you want to use the code which we provide, then hopefully you will understand what these different parameters mean. So 5 by 5 here is the dimension of a filter. If you think of that as a matrix, a 5 by 5 matrix, and you make downscaled replicas, and these downscaling can, like in this case, can lead to 14 times 14. So instead of 28 times 28, you have reduced it to 14 times 14. You keep your 32 images. You have a new convolutional layers, a new filter. You produce twice as many images. And then you downscale it again. So you have images of the size 7 times 7 times 64. And then these are sent into a standard feed-forward neural network. So the parameters you trained are the weights and biases in the convolution stage and the weights and biases in the standard neural network phase, where you just have a dense neural network, but where you have trimmed down the images. So this is the basic approach. And one of the reasons why you do this kind of trimming down is through this filtering, is that often images have strong correlations locally. So you try to keep some local features, and then you just trim down the image gradually. So as I said there, the key idea is to move away from a dense neural network, which is normally done by this affine transformation, is that you, if you're doing imaging, which is the standard application of convolutional neural networks, is that images in the neighbor pixels, they tend to be related. And so you connect only neighboring neurons in the input instead of connecting all with the first hidden layer, as you would have done in a standard neural network. So we perform a filtering, and this is often done in imaging, in sound studies, etc., etc. You have some kind of filters. And for those of you, and this is something which we don't cover here, because when you look at many of these filters nowadays, they are often tailored to Fourier series. But I know that not everybody has seen the mathematics of Fourier series. So I will just go through the more, what you might call the slightly older variant of doing convolutional neural networks. So the modern one is actually through Fourier series. Now, one thing before the era of deep learning, so how many of you have heard of the singular value decomposition as algorithm? Well, some of you have. So the singular value decomposition, this is my favorite algorithm in linear algebra. And it is an algorithm where you can decompose any matrix in terms of one orthogonal matrix times a diagonal matrix times another orthogonal matrix, even if the matrix has singular eigenvalues, or in a completely parallel statement, even if the determinant is equal to 0. So you can always decompose a matrix. And the singular value decomposition is not limited to square matrices, which will be the typical ones you encounter when you solve eigenvalue problems. So what you can do then, since you have two orthogonal matrices, is that orthogonal matrices, then the column vectors are then orthogonal vectors. These vectors can be used to make projections. So a projection operator is an operator when you square it is equal to itself. So you can actually take a matrix which is 100 by 100. You get 100 orthogonal vectors. And then you can use only the 5 first vectors to downscale an image. However, you have to do the singular value decomposition. So you have to have performed the linear algebra exercise of the singular value decomposition. And you need to keep all the information about the 100 vectors. If you have a square matrix, which is 100 by 100, then the two orthogonal matrices will have the same dimensionality. So in the example which you see here, you will see an example of how things were done in the old ages. The problem is that if you have a huge image, and if you have many of these, then you need to store all these orthogonal vectors. And clearly that becomes unwieldy when you have a huge number of images, and you have images with, let's say, 100 times 100 pixels. So the example which you see here is actually an example where I've taken an old photograph of mine, and I just reading it in so you can actually rerun these examples. And this is a color image, which I downscaled to a gray image. And it's an image which I tailored to have a dimensionality of 100 times 1200. That's the width and the height of the image. And then what I'm doing now is to downscale the image. So these K vectors, they represent the projections you get from the singular value decomposition. So remember now that if you have an orthogonal vector, you can always set up a projection operator. So let me just quickly remind you of that by switching over to the whiteboard here. So a singular value decomposition, if you have a matrix A, that can be written out in terms of a matrix U. There is a matrix which has the so-called singular values, which is a diagonal matrix, multiplied with a transpose of a matrix V. So suppose now that A is a real matrix of dimensionality M times N, then this matrix U is a orthogonal matrix of dimensionality M times M. This matrix has the property that U of T times U is equal to U times U of T, and that's equal to the identity matrix. We can rewrite this matrix in terms of the column vectors. So you would have a vector U0. This is now a vector. And then it goes all the way up to U of M minus 1. No, that one, like this. Now, what you can make then is that you can make a projection operator. So what you have then is that since these are orthogonal vectors, if you now sum over all of them from K equals 0 up to M minus 1, this is simply given by the outer product of these vectors. Okay, does that, for those of you who have seen the singular value decomposition, I hope this rings a bell. So this is the algorithm in linear algebra. You can apply this to any matrix. And when you have that one, if you now only keep the two first components, then you can then have, if you keep only the two first components, you could now write a projection operator, which is given by U0 plus U1. So remember now that this is an outer product. An outer product is a matrix. So this P is a matrix. And when this acts on a specific vector, it performs a projection based on these two operators given by the two vectors U0 and U1. So that's the way you would typically define a projection operator. And then the other matrix, this V of T, is also an orthogonal matrix. And it has the property that V of T is equal to, again, the identity matrix. So you can, again, set up a set of orthogonal vectors and define a new projection operator. So this is an extremely useful tool if you want to analyze mathematical properties of some specific eigenvalue problem, or if somebody gives you a set of eigenvectors, then if you want to project out specific components, you can use the singular vectors here. So this V has a dimensionality of N times N, and this sigma is the one which contains the singular values. So that contains values sigma 0, sigma 1, down to a sigma p minus 1, and then it can have zeros. So the rank of the matrix is defined by the singular values which are non-zero. So obviously doing this operation is slightly more expensive than diagonalizing a matrix. And if the dimensionality increases, which will be the case when you have images of high resolution, this becomes what you might say computationally expensive, especially if you want to decompose many images. So the example which you see here is an example of the old-fashioned way of performing this decomposition. So let's go back to the Jupyter notebook here. So the image I've taken is then decomposed here. So I'm compressing that. So K, I take the 5 first eigenvectors, and they are normally related to the singular values. I'm picking the largest singular values. So this sigma 0 is this output from a singular value decomposition is normally ordered so that you have the largest singular value as the first eigenstate. And then the numbers here are simply the number of vectors which I'm using in the decomposition of that image. And then I'm just computing the different ratios here. And this is actually an image from a beautiful place in Italy. It's a city which is called Volterra. And it has a history of more than 4,000 years. It was one of the capitals of the Etruscans in Tuscany. It's a kind of mini Florence, actually. If you have the possibility to be there, go and visit Volterra. And you can now downsize it. This is the grayscaled image. You can downsize it, and you see when k equal to 5, this is perhaps not that impressive. So it's pretty blurred. But then I can use the 10 first orthogonal vectors. It's getting better. Now you see there are 2 houses. And then I can keep increasing this one. I have the 21st, and now it's pretty good. So if you want to recognize, if you've been in this place before, you can most likely now even almost read what's on there. And if I take 100, then this is, you can actually read that it says Cassa di Risparmio di Volterra. So you can really, with just 100 vectors. And your matrix was more than 1,000 times 1,000. So this is the standard way by which we would typically decompose an image. But you see quickly that this becomes unwieldy when you have many images. So if you look at the data sets like ImageNet, which has more than 1 million images, if you want to store all these decompositions, then it's going to give you a huge database. And this is where CNNs, what actually paved the road for CNNs as a way to reduce the dimensionality without you having to store all these orthogonal vectors in order to keep the information. Because when you have these orthogonal vectors with the k equal 100, you can always reconstruct the full image because you have the information about the orthogonal vectors. Okay? So these are kind of motivation a little bit more for why we do this. And the thing which I wanted to bring a little bit up again is some of the technicalities which we need to deal now with in the convolution stage itself. So an example which we looked at last time was a very simple example, and I'm going to pick this up because it allows us to bring in these parameters. So there are hyperparameters when we are setting up the architecture of a convolutional neural network. One of these is called padding. Another one is called stride. Another one is the dimensionality of the filter. And another one is the number of replicas we make of the filter. So if you go back to this image, which we had in the beginning of the lecture, there are parameters like this 32, which is the number of replicas we are going to make. There's going to be a parameter which defines the size of the filter. And then there are two additional hyperparameters. So these are parameters which you don't tune when you run the calculations. So these are set and define the architecture of your network. In the same way as when we discussed standard neural networks, where we defined the activation functions, the number of hidden layers, the number of hidden nodes, etc. So let's just scroll down, and we are going to look a little bit more into these examples, which we have here, in order to motivate padding and stride as parameters. So the example which I took then is an example where we performed a polynomial multiplication. And we discussed that last week as well. And I'm going to repeat it a little bit in different formats, almost ad nauseam, because there are some technicalities here which are useful to understand a little bit better. And because this translates into the way you actually map an image to a lower image through a filter. So what we are going to do now is to treat this lower dimensional polynomial as a filter. We're going to interpret it like that. But the product which we have is a fifth order polynomial when we multiply these two guys. So you can obviously just write it like P times S, and then you get Z as a polynomial. Or you can be a little bit smarter. Actually, you don't multiply it like this when you do it numerically. That would be a horrible way of performing multiplications of polynomials. You would actually set it up in a smarter way. And the way you would do it now is to group these different terms. And you see now that the alphas, they run from 0 to 2. So that is a vector of length 3. The betas run from 0 to 3. So that is a vector of length 4. You can write this where you sum from minus infinity to plus infinity. And that is what you would call the general expression for convolution, the way you would look it up in textbooks. However, as you see here, we have only 3 components here and 4 components. So running from minus infinity to plus infinity, in this case, is just a waste of time, right? You will have lots of zeros, and you would have to define a huge vector. In addition, you cannot deal with infinitives. So you could rewrite it like this, but we're going to make a simplification. And I'm going to rewrite these coefficients now in terms of another way. The way which often is used is to rewrite this in terms of a matrix times a vector. This is actually the pre-Fourier transformation way of doing it. Actually, when you do Fourier transformation as well, you end up with these Toeplitz matrices. But you can rewrite this in terms of that matrix. And then we know that convolution is a commutative process. So you can rewrite it like this. But let's now move down a little bit, because this is something which we did last week. There are some links here to Fourier series and how they are used in convolution and the convolutional theorem. But we are going to take this expression here and we are going to rewrite it like this. Because as I said, there is no point in going from minus infinity to plus infinity. That's a waste of both time. And in addition, we cannot allocate memory for that. So I would write this convolution process like this. Now, if you look at this, if I have I equal to 0, then K runs here up to 3, minus 1. So I would then have 0 minus 2. So there would be an element of x minus 2, which I haven't allocated. So if I want to use this expression here, so that means that if you allocate memory, then you're trying to access an element which is not defined in your memory. So that's one problem. The other thing is that you can actually rewrite this equation here by introducing the concept of padding. So let's see how we can do that. So you see now that when I do these calculations, you may have to access elements which would not be defined if you now have a vector where you run from j equals 0 up to 3 for these x's and 2 for the w's. And when I is equal to 5, because you have a fifth order polynomial, you will have elements with x4 and x5, which also are not allocated. So this leads to one of the things which is called padding. So let's take a look at that on the whiteboard so that we have everybody with us here. So let's now bring up this example and try to set it up in a slightly different way. So what we have now is this polynomial, and we have set up a simple polynomial of degree 2, a second order polynomial, which is multiplied with a third order polynomial. And if we now look at the expressions which we have, so we have a j, which runs from 0, 1, 2, and 3. So we have these quantities x0, which is the same as this parameter which we defined in the previous equation, which was given by this beta 0. And then we have x1, which is beta 1. We have x2, which is beta 2 here. And then we have x3, which is beta 3 here, like that. And then we have the other vector, which now represents this filter. So that's all weights, as they're often also called. So we would have a k equals 0, 1, and 2. And we have this w0, which is alpha 0, and w1, which is alpha 1, and w2, which is alpha 2 here. And then we have the expression for y of I, which now was set up to k equals 0, up to k m minus 1, where m is the max dimensionality here. And then we have n equals 3 here. Actually, sorry, this is wrong. This is actually, we have 4 elements, sorry, 3 elements, and we have 4 elements here. So that vector has a length, one vector has length 4 and the other one has length 3. So if I now allocate memory for these 2 vectors, then if I now calculate y of 0, you will see now that there will be a term here. So we would have a y of k multiplied with x of I minus k, which is just a simple way of writing the general formula for convolution. So if you do this now, you will see you would have a term w0 times x0. And this is what we had before, alpha 0 times beta 0. But then I get a w1 multiplied with an x minus 1. Okay? But then I have plus a w2 multiplied with x minus 2. So these two are not defined. And if I take the final term, because my i's, the term I, that has elements from 2, 3, 4, up to 5. So that has 6 elements. So I have a fifth order polynomial. When you multiply a second order polynomial with a third order polynomial, you get a fifth order polynomial. So the indices for y, they just span from I equals 0 up to 1, 2, no, sorry. Again, it's me not being able to count properly here today. That ends at 4. Sorry. So if I look at the last one, that will produce, if I take y of 4, that is going to give me a components x with x of 4 and x of 5, which I have not allocated space for, because what I have allocated space for are these components here. So what could I do then? Now, what I could do now is to add 2 new elements to the vector x to the right and to the left. And that leads to a hyperparameter, which is called padding. So I now introduce padding. And this is one of the reasons why we introduce it. There is another reason as well, which you will see when we perform the filtering with a matrix times a matrix. And you will see why this padding becomes interesting as well. So what we could do now, if we look at the vectors here, we could now have we have the previous ones. So we have x0, and we have x1, and we have x2, and we have x3. But we need now simply an x4, and we are going to add an x5, and then we are going to add a new one here and here, so which will be an x minus 1 and an x minus 2. And then we can always relabel here, right? So we can define a new vector. So we are adding 2 here and 2 here. So we have a p, this parameter p, which is equal to 2. And in total, what we get then is 2 times p additional elements. So that leads to 2 times p additional elements. And these elements are just 0. So this one is 0, this one is 0, and that one is 0. So what I do now is simply to translate this x into a new vector. So we have an x, which now goes into an x tilde. And then we're just going to use x again, right? Because this is just a dummy variable, and you can call it whatever you want, right? So what we do now is that we define a vector which has a length 8. So I'm just going to define this x0. So this is a tilde, x1, and then x2, and then I have my x3, I have my x4, I have my x5, so that's 3, and then we have x6, and finally x tilde 7. So these guys are 0, 0. This is now given by the old variable, beta 0, beta 1, beta 2, and then I have beta 3, 0, and 0. So that's my new vector. So the only thing I've done is just to increase the length of it, because this allows me now to perform the mathematical operation without worrying that there may be array elements which are not accessible in memory. So what I would end up doing then is then replacing the previous formula with a new formula. And the new formula is going to look like this. So my y of I is going now to be given by a sum, which is the same as before, for up to k equal m minus 1. And then I'm going to have my w of k, but this is multiplied with x of I minus, and now I have m minus 1 minus k. And this is going to be the expression which we will encode when we are setting up the convolutional operation here. So that gives me, let me see that I wrote things correctly on off here. It should be plus here, obviously, plus minus m minus k. So you can now see if we go back to the Jupyter notebook. So let's go through the some of these definitions again. So padding here, we have introduced 4 new elements. So that means we augment the length of x from 4 to 8. And these are the elements which we get. And then we can rewrite the equation like that. So if I pick one of the components now, this y of 4, then I would get x6, which is 0, multiplied with w0. And then I have x5, which I have defined earlier, which is now the same as beta 3, which is this one. And then I have x4, which is beta 2. So this was the original formula, beta 3 alpha 1 plus beta 2 times alpha 2. So this is the 4th order term. And you see now that you have a third order term times a first order term, a second order term times a second order term. So this gives us back the same equation which we had before. So padding, it becomes a parameter which we have in the setup of a convolutional neural network. And there are further examples here where when we looked at the fifth order term, there was actually only one term in the original expression. And you can see that you recover that one by this new formula. And then you have the zeroth term, which again is just alpha 0, beta 0. And previously we had these terms which you see here in terms of x minus 1 and x minus 2, which were not defined. Now, there's another thing which you can do. If you look at this expression here, there's nothing which hinders you in rotating the filter or interchanging the filter. So what you could do now, if you look at the expression which you have here for the filter, so you have x2 times w0. This is just one of the terms. What you could do now is to read up a new filter, w tilde, which is equal to the original w2. And you would do the same with w1 and the w0 which you had. And if you do that, then you can rewrite it like this. And that looks very much like a dot product, right? So this is a when you come to matrices, you will see these as rotations of a matrix. Now you're just flipping the filter here. Okay? So this is the kind of tricks which you often do in order to have efficient setups of the process of convolution. So that means that you can then rewrite that sum as a dot product of x of I plus m minus 1 for element y of I, where you can simply view this as a patch of x of size m minus 1. So this is the standard way by which you do that. There is another parameter which we are going to introduce, which is called a stride. So we're going to look at that after the break and look at how we define that one and why this is also an important parameter. So in general, this expression which you see here, if we now go back to the infinite sums, is normally rewritten, and this is the way it's done in essentially all libraries. If you go to PyTorch, if you go to TensorFlow, you rewrite this in terms of pluses here. So this is just you redefining the vectors. And this is seemingly more efficient computationally. And it's normally referred to as convolution, but it's not the same as convolution. It's almost the same. But then you get the same padding rules, etc. If you're doing two-dimensional objects, you typically have, again, this kernel or weight of filter, whatever you want to call it. And this is the standard expression where we simply now take the one-dimensional case. So everything you've seen in one dimension is something you can translate easily to two dimensions. So you will simply have this expression, and since it's a commutative process, then you would typically rewrite it like this one, because that's more straightforward to implement. So just keep in mind, if you look at what we are doing here, if you go back to that example we had with the matrix vector multiplication, so you could rewrite it like this, which is a 6 times 4 matrix multiplied with a 4 times 1 vector. But you can rewrite that in terms of a 6 times 3 matrix multiplied with this vector. So it's commutative. So the way you order this one can have a significance for the number of floating point operations you're dealing with. So I hope you see this is what we might call the basic mathematics of the process of convolution. Okay? So I hope you don't mind if we demystify some of these things, because normally what you would see in basically all textbooks with applications is that we implement this with no further explanations. And typically, if you then use cross correlation here, this is what you implement. So one thing I put up here, and I'm going to use this example to introduce yet another hyperparameter, which is stride. So if we now look at suppose you have this input here. This is often called a volume input or input volume. And we are having a filter, a 2x2 filter. So what does that mean? So what it means is actually that we now have to be a little bit careful with the way we perform this filtering. So you could now take this subblock here, the first 2x2 subblock, and perform the convolution with a filter. Then you can move one step. That means stride equal to 1. So you move one column here, and then you act with a filter on this subblock. Then you move down one step, one row down, and then you perform the filtering on this piece here. Still stride 1. You just move one column, you slide one column at a time, and you slide one row at a time. So the way you define these parameters is actually important because that depends on the size of the matrices you're dealing with. Because sometimes you may actually not get an operation which runs through all the elements. So when you perform the convolution here, or this filtering, you with stride equal to 1, so we move one column to the right, we slide one column, and we slide one row. Then this operation here gives us a 2x2 output. So we have reduced our 3x3 input to a 2x2 output. Okay? So stride is this parameter which now sets up how we slide in the input matrix. But you should see another thing here, which is actually a little bit important. And that tells you why padding becomes important here. So if you think of x0, x0 is one of the corners. x02 is one of the corners. x20 is one of the corners, and x22 is a corner. If you now look at your convoluted result, you will see that x0 appears only in this first matrix element. However, x01 appears here, and it appears here. Similarly with x10, which is another one of these results not on the corners of that matrix. So these are the corners, x00, 02, 20, and 22. These corner results, they appear only in one of these guys. Whereas the other elements, they appear in all of them or many of them. So what is often done then is to add a set of zeros outside the matrix. Because then when you perform the convolution, then you will get these variables x0, the corners, they will appear in more of the matrix elements you get. So the point here is actually to keep some information and avoid that specific types of the image just appear in one specific place, because that information may be lost. And maybe if this is a house or something like that or whatever, a kind of structure where you want to keep information about the corners, then this is where padding comes into play and allows us then to spread this information out in the convoluted or the result of the convolution. So we are coming back to that after the break. We are going to jump back to the whiteboard, and then we will look at how we can apply padding, how we apply stride. The other thing which we will take a look after the break is an excellent website by two guys from the University of Milan, which illustrate the role of different types of padding and stride and how that can transform your output. So after the break, we're going to take a look at that one. They actually give you Python codes where you can play around with different stride and padding values just to get a feeling of how the information is being transferred. Any questions so far? It's perhaps not the most exciting topic, but it's important to understand how this comes into play when you are setting up the architecture of the network. Because these are input parameters when you run either TensorFlow or PyTorch or any other libraries, or if you run the code which we have available here. So what we looked at before the break was a case where we have an input volume, which is given by a 3x3 matrix. So this could be an image, a grayscale image with 3 pixels times 3 pixels, which would be a very blurred out image. I don't think we will be able to see much out of that. And then we have a filter now with what we call a stride equal to 1, where we simply multiply out with different blocks, the sub-blocks, 2x2 blocks. And in each case, we move just one step to the right here and one step down. So we are setting then up what we call a convolutional stage with a stride equal to 1. Now, the thing we discussed also was in this process, the corner values, they are just appear in one of the new matrix elements. So we have a filter down the dimensionality down to a 2x2 matrix. So this will be the output of the convolutional stage. And the thing we saw now is that we have this x0, which is one of the corner values of the original input volume, which now appears only in one of these matrix elements. So typically when we add padding to this, so in the previous case, when we looked at the one-dimensional vector, we added padding simply because we wanted to avoid having vector elements which were not allocated in memory. And then we just redefine the vector. Now here, there is an additional feature which comes in, and that is that we would like this information to be passed to more places in this filtered down image. Before we go back to the whiteboard, what I wanted to say is that typically these operations, they are normally not written out like this, but they can be written out in just rechanging the way we set things up. So we could define a vector x prime of length n, and we could define a matrix W of dimension 4 times n. So that matrix is actually this Toeplitz matrix, which we defined before. And then we will simply have this matrix multiplied with this vector of length n. So you have a matrix of length 4 times n multiplied with a vector of length 9 times 1, or dimension 9 times 1. That gives us a vector of length 4 when we perform the matrix vector multiplication. So that gives us a vector of length 4. So that means that instead of us writing this out as a matrix, the same elements, we write it out as a vector of length 4. So that would be just the difference. And this is often the way these operations are encoded, because this type of way of setting it up gives a more efficient coding of the operations. Now, if we go back to the whiteboard a little bit and take a look at that matrix which we had. So one way to avoid the problem that the corner values, so let's just write down the matrix here. So we had an x00, x01, x02, and x10, x11, x12, and then x20, x21, and x22. And what we saw in that case is that the corner values, they appeared in only one of the matrix elements or vector elements. So what is typically done then is, so we had an operation where we had stride 1. This is what we put up, s equal to 1. So when we perform the multiplications, the first one was done with this block here. Then the next one was done with this block. And then we move down to this one, and finally to the final sub-block here. So this is stride equal to 1. Now you can see now if you were to set stride equal to 2, that means you would actually, when you've operated on this one, then you would try to operate on that one, but you wouldn't have all the elements which are needed. So one way, if you have stride equal 2 in this case, is to add some padding. So in the previous case, we had padding equal to 0, but we could say we have a padding equal to 1 now. So that means that we would simply augment the size of the input volume by adding zeros here. Now, zeros don't harm because we would then simply just multiply with zeros. So it's when we look at the final result, but what happens then is that the points which were corner points, they end up as inner points, and they will be replicated in more boxes now. So one of the first boxes, when we do this padding, it's as we did in the one-dimensional case. What we have now would be a block like this, which is operated upon. That would be the first block with a filter. The next block with a filter would be this one, if we have stride equal to 1. And then we would simply move on to the next block here, and the final block here. And then we would step down if we have stride equal to 1. And if we now go back a little bit, but before we go back, let's now look at the type of parameters which we end up with when we are setting up a convolutional stage. So let's just, so parameters in the convolution stage. So these are parameters of the architecture of conv stage. So one is a parameter which I'm going to call for K, which is the number of filters we set up. Another parameter which I'm going to call F, which is their spatial structure or their spatial extent. So in our case, we had a 2 by 2 filter, which means that F is equal to 2. Then we have S, which is this stride. And then we have P, which is the amount of padding. One thing you should keep in mind, convolutional networks and the application of these is a kind of art by itself, because the filters are often tailored to specific images. So if you want to recognize buildings, there are specific features of buildings. If you want to deal with facial recognition, there are specific traits you want to have. We don't have whiskers, but it's like cats, so we don't need to encode that in the filter. But there is a nose, there are 2 eyes, there's a mouth, etc., etc. So the filters which you have are really, in a certain sense, hand-tuned to a specific case. And you will often see in the literature that you have dedicated filters for these and these scopes. So just keep that in mind. So specific research fields may apply different types of filters. But the basic structure is the one you see here. And if you don't know which filter to apply, what people do is actually they take the default ones, which are often encoded into the different libraries. So these would be the parameters which you would have. We have then an input volume. And that input volume, which is the input image, this has typically a dimensionality where we have the width of the image. And this is multiplied with the height of the image. And then we have what's called depth, which is normally the number of colors which we have. So if you have a gray scaled image, it will be 1. If you have the 3 classical color channels, red, blue, and green, then you would have 3. So this is normally called the depth. And then when we look at an application of a filter, so a filter produces a new image. Filter produces a new volume. You can call it image or volume or whatever. Produces a new, you will often see this being called a volume. And that has a dimensionality where we have a new width, a new height, and a new depth. And there is a simple formula for these equations here. So this W2 here is given by the original one minus F, the extension of the filter. So these filters are normally square matrices. And then we have the padding, 2p, like we had in the one-dimensional case. Now, remember in the one-dimensional case, we added 2 times p. We added 2 values to the left and 2 values to the right. So in total, we ended up with 4 new elements. And then this is divided by the stride plus 1. So this is not a number 5. It's actually my attempt at the letter S. And this height is normally given by H1 minus F plus 2p divided by the stride plus 1. And then this D2 is normally given by the number of filters which we produce. So these are the typical setups which you have. So if you now look at an example, or let's rather look at the typical filters or common settings which you will encounter in the literature. So we would typically have F equal to 3. You can have S equal to 1, padding equal to 1. You would find F equal to 5 and S equal to 1. These are some of the typical settings. F equal 5, so a 5 by 5 filter and a 3 by 3 filters are some of the most commonly used ones. And P, here we can say whatever fits. And then we have an F equal to 1, and then S equal to 1, and then we have 0 padding. So if we go back to some examples, you could now think of us having an input volume, which is given by 33 times 33. So the input is 32 times 32 times 3 color channels. And then you could decide that I want to apply 10 5 times 5 filters. So I'm producing some kind of 5 scaled down images, which hopefully contain as much information as possible. And then we have 10, so K is equal to 10, 5 times 5 images. Oh, sorry, not images, but filters, which we apply to this. And I could now decide that stride is equal to 1 and padding is equal to 0. So when you run this type of calculations, you actually have to tune the network so that you actually find the best reproduction of the data. So if you want to look at a classification problem, you're looking at the accuracy, how well it classifies. The ideal accuracy is 100%. So you would tweak the network parameters so that at the end, after many, many different runs and trainings, you actually get the right parameters. So at the end, everything becomes numerical experiments. And the kind of values which you see here are values which many practitioners have found strike a balance between the accuracy you want in a classification problem and the number of CPU cycles you're willing to invest. Keep also in mind that many of these networks, the big ones, they are trained by companies which have access to high-performance computing facilities you can only dream about. So much of the big training is done by Google DeepMind and other companies, sadly. the electricity bill of these companies are electricity bills which we cannot handle, period. There's a city in Oregon which actually allowed Google to build a facility. And that facility swallowed 80% of the electrical consumption of the city. So the city had to get additional electricity. We have a small municipality here in Norway which allowed TikTok to establish itself. And suddenly, these people from this local community, and I suspect that they are under this is a political statement which I shouldn't make. I suspect them to be under the influence of the fumes of the akvavit production, because the city makes akvavit. And they suddenly discover that they have no electricity left, because TikTok takes all the electricity. So when you have this kind of big networks you want to train, the electricity bill actually is amazingly high. Sorry for this digression, but sometimes it's important to keep in mind because it can be frustrating to run things on your laptop and you're just running with very small networks. So keep in mind that the big ones, they are trained on really high performance computing facilities, dedicated ones. Okay, sorry, that was a digression here. But if we now look at this example, we can now count the number of parameters we need to train. So parameters to train. If we now look at the image itself, so every filter now has 5 times 5 weights. And we're having 3 color channels. So we have times 3. And then each of these filters has a bias parameter plus 1 here, which is a bias parameter. So that means that in total for the filters, we have 76 weights and biases, which we need to train with backpropagation. Then we have 10 filters. So since we have k equal to 10, that means that this filter operation leads to 76 times 10, which is a 760 parameters to train with backpropagation. Okay, so that's a typical example. And when we scale it down, the new dimension of the image, if we take away the color channels, so the new dimension is then a h, since we are taking a square matrix, so the height and the width have to be the same. They're given by the width of the original one minus f, which is equal to 5, plus 2 times p divided by the stride, which is equal to 1, plus 1 here. And that means that the dimensionality becomes 28. So H2 is equal to W2 is 28. So what we are getting then is in total, we have 28 times 28. So we went from 32 times 32 times 3 times, and since we are now making 10 images in total. So this is an example of us setting up a convolutional filter. We produce replicas. Then after this, we send this through a ReLU operation. So we produce a new output. And after that, we have the pooling stage. So we have done the convolutional stage. So that means we have the convolution. This feeds into the ReLU stage, where we simply pass the information through an activation function of the ReLU type. So that just transforms your output from the convolution stage. Each element is now transformed with a ReLU function. And the next step is actually the pooling stage. So pooling is a dimensionality reduction part. And the way it functions, there are two ways of doing that. So one is called max pooling, and the other one is called average pooling. These are the two standard ways of doing that. There are other things which we haven't discussed yet, like dropout, parameter sharing, and so on. These are additional features, but a pooling function, what it does, it replaces the output of a certain location in the image with what you can call a kind of summary statistics. And max pooling is often the one which is most used. So what happens then with pooling, you could now think of, so let's look at this final stage, because the ReLU stage is pretty straightforward. This is just you sending all the output from the convolutional stage to through a ReLU function that changes the output. Then you have the pooling stage, which is a dimensionality reduction part. So what you have then, suppose now that you have an input, let's look at 4 nodes here. So you have an input where after the ReLU, this node 1 has value 0.1. This node 2 has value 1. This node 3 has a value of 0.2. And the final one has a value of 0.1. Now, one thing which is also typical for these convolutional neural networks is not a dense connectivity. It's often a sparse connectivity. So this is what comes out. What this block here is what we have as output from the ReLU stage. The numbers are just numbers I've made up. Now, this feeds into the pooling stage, so which we can label as this one. So we have the new node here. So we keep the same nodes, but they have a sparse connectivity. So this node here connects only to these two. So that's the border node. Node 2, so they connect only with 3 nodes. If we had a standard neural network, there would be a connectivity with all of them. That would be what we call a dense connectivity. But what's typically the thing in a convolutional network is that you have a sparse connectivity. Then this node 3 connects with 3 only. And finally, the corner ones can only connect with 2. Now, what it then does is that it picks the max value. So if you look at node 1 here, it feeds in here, but this gets also an input from node 2. But then you take the largest value, which is 1. So that means that this outputs 1. If we now look at this is node 1, node 2 here. If you look at the next one, that receives 0.1, 0.2, and 1. And you pick only the largest value. So this also produces 1. And then you see that the next one also produces 1. And the final one produces 0.2. Now, what happens then is that there is no reason to carry 3 ones. So you would typically reduce this further by just keeping 1 of these nodes. So you're actually reducing the information further. So in this specific case, instead of carrying information from 4 nodes, you reduce that to 2 nodes only. So pooling is a way to reduce the dimensionality of the problem. And this is the final stage. Now, if you're happy with that, then you can feed in your output from the convolutional stage, which has these 3 elements, the convolution itself, the feeding through an activation function, and then the further dimensionality reduction. So there is a nice figure which I took from the textbook by Rashka, which you can see in the Jupyter notebook here. So if we scroll down, you will find the information which we discussed here in the convolutional stage is summarized here as well. You can find the ways you calculate this information. So if you then look at the typical pooling stage, so this could be, and as we said, this pooling function, a pooling function replaces the output of a certain location. So you would say now you have to have these locations here. So this would pick 8. So you actually reduce the dimensionality here by simply picking the largest values of these regions. So it's a way to downscale the information which you want to carry with you. And then you can also do an average one, where you can take the average from these blocks. And then the average from this block would be 3.78, 2.33, and 3 and 122. That's one of the other ways of doing that. So if we then go back to the image which we had in the beginning of the lecture today, which is also an image which I took from this textbook by Rashka. What we have now is a series of convolution, and here they have skipped the Relo stage. You have the pooling part, which reduces the image further. You have a new convolutional stage, so you can add these bits and pieces as you want. And then you end up with a final neural network, which can be as deep as you want. So you can have a standard feed-forward neural network where you do the training by backpropagation, as we discussed earlier. So one thing which I want to do now is to show you, before we dive into our own code, how you can do this with TensorFlow. Because many of you will probably use either TensorFlow or PyTorch. So who has landed on TensorFlow as an API? Not that. PyTorch? Okay, some of you have. So PyTorch in a textbook by Rashka, you can actually find a very nice way by which you can build up your network. And we will discuss these things as well. But what I wanted to do is to point to you, because in the lecture notes here, you can run the case with TensorFlow as well. You have access to the Jupyter Notebook from Rashka's book. So feel free to get inspired. But I'm going to look at my TensorFlow implementation. And I need now to find this one. And this tells you a little bit on how you can set up your own notebook here. Not that one, but it should be this one. Have too many windows up here. Nope. Yeah, this is the one I wanted to discuss. So the first example using TensorFlow is one which takes the MNIST data set, which is kind of classic now in the literature. So these are the handwritten numbers. The original data set has some 70,000 images, which all are 28 times 28. Now, for, how to say, purposes which deal more with time and to be able to run it during a lecture, I'm using what's called a scale down variant, which now gives you images, roughly 1,800 images of dimensionality 8 times 8, and only one color channel. So the human capability, and I'm not sure if I agree with that number, but according to experiments, the human capability has an accuracy of 98% to recognize these images. I think that may have to apply to the original data set. So, because I have problems when I look at some of these images to actually recognize them. I think that 98% applies to the original handwritten numbers. So what you have is close to 2,000 images like this. And when you want to use Keras and TensorFlow, you need to include You have the data sets, etc., layers, models. So this is a sequential network. So everything we do is sequential in this case. So you start with the input volume, you feed it to the convolutional stage, and then you keep moving on. You have dense networks. You have to define the optimizers you want to use. You have having categories. You have 10 categories. The 10 handwritten numbers from 0 to 9. These are the categories which we deal with, which means that the cost function is normally called this categorical cross entropy. Here we include the regularizers and optimizers as well. And I split the data into train and test. So it's a typical thing to, as you know, everybody studied machine learning. We know that roughly 70–80% of the data used in the training, and then the remainder is used to test the model. So when you run with Keras, you can see now the way you would set it up here. So I'm setting up a convolutional two-dimensional layer. So this is, I don't need colors. If you have colors, you need 3D. I'm setting up the input shape, padding. These are just the information. I'm using the Relo activation. And then I'm using a regularization term, which is of the L2 type. This defines my scaling of the pooling size. There's a 2x2, as we discussed earlier. So these are parameters you can define. It has a layers which flattens it. And then, so there is only one convolutional stage here. So I have the convolution, the 2D convolution. I'm using, these are the filters. So you can actually look up the definitions, what these filters actually mean. So the manual is actually pretty good, where you can define, where you can find what kind of filters you have access to. The pooling stage is done here. Here we flatten the information, and then this is sent into a standard neural network. The optimizer for the gradient descent and training of the weights in backpropagation is a stochastic gradient descent, just a plain one, which is here. The metrics for success or failure is you summing up the number of correctly classified images. So that means you count the correctly classified and divide with the total number of images. That is the simple type of accuracy. So 100% is the ideal here, right? And then you have to define further parameters like the number of epochs and the batch size when you do the training. We are setting up ranges of the learning rate from 10 to the -5 to 10 to the 1. 10 to the 1 is not the best value. And then you have a lambda, the hyperparameter. So these are parameters you tune. In this specific case, then, when I run the calculations over all the parameters, you can see the visualization here of the training accuracy for all the types. So on the y-axis, you have the learning rates, 10 to the minus, the first one, 10 to the -5, 10 to the -4, 10 to the -3. And the package is actually doing pretty well for most of the values, except for lambda hyperparameters of 1 and 10 to 10. And you see there that the accuracy is not that good. So this is on the training data. So the accuracy on data which has not been included in training, so you take the parameters of the network and you apply them to data. You see now that you get an accuracy of 98% roughly. I think I wouldn't have been able to reach 98% on those images. But these, remember now, these are labeled images. So when we come to generative models, we are not going to deal with labeled data in most cases. So somebody has actually written that this is number 1, number 2, etc., etc. There is actually not very much machine learning in labeling data. So when you look at ImageNet, this huge data set, there are actually people who have labeled the data. There's another data set which you can look up here, which is called the CIFA data set, which is also a famous one. And that one is contains some, in this case, 60,000 images, I think, roughly. And these are images of many different things, trucks. It actually selects randomly the output, because in this case here, I got many frogs as output. Another time when I run it, I got many trucks. So somehow the output here, when it visualizes a data set, is somewhat random. But then you can train them all. And the thing which is nice with these libraries is that it tells you also how many parameters you have. So like here, we can now train a convolutional neural network. We're making 32 images. And then we have a filter, which is a 3x3. So this is a typical size which you have. And the input shape is an image of 32 times 32. We are training 32 images. We have a max pooling of 2 times 2. And then we have a new convolutional layer where we now produce 64 images. And then we still have a 3x3 filter, the same type of convolutional layer. And then there is even an additional convolutional layer. So you can actually stack up as many convolutional stages you want. And you can see the number of parameters here when you do the first one. So this is the output shape, because we have a 32 times 32. And in this specific case, we have a 3x3. Yeah.
Are you using color images now?
Yeah.
But you're using color 2D, so what does that do with the...
Yeah, so these are actually scaled here, actually. So it's grayscale, images are being grayscaled. So I think that's what is done in this here, yeah. So it tells you the number of parameters you end up with, the outputs, when you now perform pooling. These are the output shapes. So this is very useful because it tells you, so in the convolutional stage, that's where you have the weights. You're now adding more images, so you have more weights to train. So the total number of parameters now is given by, these are the trainable parameters. And keep in mind now that stride and the padding, the number of images you're making, are actually fixed by you in the architecture. So when you want 64 here and 32, this is something you fix. F, which is a dimension of the filter, is something which you fix. So that is your architecture, in the same way as you define the ReLU function before you submit to the pooling layer. So these are parameters which are not changed when you run the calculations. So in backpropagation, you would then train here 896 weights. Here you would have close to 20,000, and here you would have close to 40,000 weights. So in total, these are the parameters. And then you can then add you flatten it, and then you have a dense layer. And you have again the activation function as a ReLU. And then finally, you have an additional dense layer. And that gives you all the parameters for the dense layer, which are 65,000. And here we have 10 classes of outputs: trucks, frogs, cars. I think there are 10 types of outputs which you get, or categories. And that gives you the total number of parameters which you need to train. So this is just an example on how you can set it up. If you go to PyTorch, you have similar setups, except that then the nomenclature, the way you set it up and call things is then done slightly differently. But you have a convolution, 2D, 3D, you have the flattening, you have the dense neural networks, etc., etc. So this kind of basic structure is the same one which you would find if you were to use PyTorch. Okay, so this is about setting it up. And I think unless you want to go through the numerical path in project number 1, so we had people every year who want to write their own codes, I would typically recommend using either PyTorch or TensorFlow in the analysis of the data which you have. If not, We have a code example, but I see that time is running out. So maybe we stop 5 minutes ahead of time. So I'm giving back 5 minutes to you guys, but I may take them back later. So next week, the idea is to start with this code which we have and just discuss it a little bit, the structure of it. There will be repetitions on how you do the filtering. And then we will start with recurrent neural networks, which for those of you who want to solve the differential equation type of problems, this can be very relevant. For those of you who want to look at large language models, this was actually the typical entry point for that. And then after that, before the Easter break, we are going to look at autoencoders. And that will bring back to life again the singular value decomposition and the principal component analysis. And that defines what we will do before the Easter break. And after Easter, we are going to look at generative models.